welcome to this demo on CEM One software. So first we'll open the software, and once we open the software, then we'll get this folder like this. So here you have to select the visual environment, and then you have to select the visual environment 13.0. So it is a license software, so you have to put the address of the system where the license is installed. So it is 27000@CEM. Then click next, and it should so this license is taken. So after this it will open the software. So when the software is opened, then we have to select this electromagnetics, because our simulation are going to happen here, and make sure that all these are checked here. So select electromagnetics and click on OK. So here this window will open, and in this window we will open the project file that we need to simulate. So we will be doing three simulations. So I'll explain those three simulations here. So we'll have to click on open project, and then we have to go to the folder where we have kept our this projects. So I'll just directly open my folder. So it is so this is the three we are going to do. One is dipole antenna, one is magic T, one is antenna. So this dipole antenna I will open and will select. So this will open a file. So this is a dipole antenna. You can see dipole antenna is nothing but a long wire, only simple wire. So if I zoom out this one, you can see this is a dipole antenna. Okay, and this can move also, and we can rotate this also. You can in different direction if you want to view different perspectives of this. And these are the parameters of the dipole antenna that is being designed. So part 1 is nothing but your antenna, okay, and then nodes. So different nodes are being used for designing this. So it's a design part which is not here. And then material, we have, this is one material. This material we have taken, you can see metallic wire. This metallic wire means dipole is basically a conductor, and it is taken as a metallic wire material. Okay, and then medium. So this medium means external medium. So it is taken as air actually. So external medium means in which the dipole antenna is placed. If you simulate, then how it is going to be placed. And frequency. So in frequency, what it is taken? So frequency is taken from range 2.5 to 3.2 megahertz. Sorry, 250 megahertz to 320 megahertz. So 250 megahertz. So it is 2.5 into e power 8. It's written. That means it is 2.5 into 10 power 8. So that is effectively 250 megahertz. And the antenna is designed at 300 megahertz. So we'll be simulating it from 250 megahertz to 320 megahertz. So if you want to change this frequency also, here you can go to this interval, and you can add the frequency points here also. But will not add, it is already added, so will not add that, that's fine. So then excitation and sources are given. Okay, so source is given with 50 ohm of impedance, and the source is given at here. You can see this yellow point here. So at the middle of the antenna, the source is given. So this is how it is there. Now we'll go to the simulation, how to simulate that. So before that, let me tell you how this antenna is going to radiate. So basically dipole antenna are omnidirectional antennas, and it radiates in the all the direction of the antenna. So if you see, this is z axis. Basically the radiation will happen in the xy plane. Okay, so we'll see the radiation that will happen in the xy plane. Now how to simulate this? So after opening this project, so here you have to go to CEM is written. Here you have go to job manager, and then just press run. Okay, it will ask for the license. Then you click on the next, and it will start simulating. So basically this is simulating. So what the simulation exactly happens in the back end, it solves so many of equations based on Maxwell's equation, and different methods as well, like method of movement and frequency domain, time domain. So it is completed. Now you can press any key to continue. So this simulation is done. So after that, we need to see the results. So how to see the results? So we have to click here on the application, then we go to viewer, and in the viewer part, we have to import the result. So when this antenna is simulated, so it will create one folder which is the extension is EHRF5. So we have to open that file. So for that we need to go here, file, and then import plot. Okay, so here we have to open that file. So where is that file? You see, this is the folder where I means imported my project, and in the same folder this dipole.erha file will be created. Okay, so you can open this file. After opening this file, we'll see here it is shown that input impedance, input power, reflection coefficient, VSWR, voltage standing arm ratio you can plot. So first we'll see the reflection coefficient, which is one of the important parameter, and here in the complex data we have to select this dB, 20 dB scale we have to select. Then you press click on plot, so it will plot this. You see the frequency that we have taken from 250 megahertz to 320 megahertz, it has plotted, and the resonating frequency is, if you click here, then it is showing the resonating frequency here. The point value is okay, so this x value is 2.83. so this whatever I have taken here, the minimum y value is at 2.83 in that means 283 megahertz. Okay, that means this means 283 megahertz this point value is, and here the y value is how much? Y value is minus 15 dB, and for antenna it should be minus 10 dB, below minus 10 dB. The S11 parameter, this is, remember, this is S11 parameter. We can see the voltage standing wave ratio also. Here we can select voltage standing wave ratio, then you, where to plot, you should select new window, otherwise it will just coincide with the previous plot. So next you click for plot here. So this is, first one is your S parameter and the second one is your voltage standing wave ratio. Here it is written voltage standing wave ratio. So what is the value here? For voltage standing wave ratio, the minimum value is how much? The peaked value 283 megahertz, and the value is around 3.1. So VSWR is 3.1, so it can be in that range. Actually the ideal case it should be 1 to 2, but in some cases it becomes high. Next is reflection coefficient done, VSW reflex VSWR, then input impedance. So as the antenna input you have given as 50 ohm of feed, that means the port you have given 50 ohm, so the antenna input impedance should be near to 50 ohm, near that range. Then only the antenna will have maximum power transfer and it will propagate. So you see the impedance also. Okay, so this impedance value at 2.83, so at the peak point 2.84. So here it is around coming 37, 37 means 37 ohms. Okay, okay, so this is complex data, linear, plot this linear value. Okay, so like this I'll delete all the values. Actually you should plot the linear, not the dB scale. Only dB scale is only for the S parameter, so I'll select input impedance, the linear, then plot. So you'll see here at 2.83 the value is 70, around 70, 2.84. then if I go to 2.83, the value will come near to the 50 ohm. So how near it comes to the 50 ohm, that much of good. So this value you can get here, it is written. Next, if I select your voltage standing arm ratio, then complex data, okay, VSWR, if I plot, it will give you that value. This is voltage standing arm ratio. You can maximize this also here, and you can see the VSWR value. Minimum is at 2.83, and a 1.3 is the VSWR value. So it is good result. Okay, so then you can close this. After this, what we can see? We can see the radiation pattern. So how to see that? So to radiation pattern, we have to select this result file. This is the result file. Okay, select this one and then select this contour. After selecting this contour, we will see two things here. One is node, one is spherical grid. Okay, so the spherical grid means what? For radiation pattern we need a sphere. Inside the sphere it will calculate at every position what is the E field value. So if I collect far field here, so this is the radiation pattern here. So as I have told you, this antenna will radiate omnidirectional and it will be in XY plane. So you can see it is Z direction is the antenna and it is radiating in the XY plane, and here you can see this is the maximum value of E field and F field. So we can change this value actually. We can this is done by a factor of 1, but we can change the factor. I can either can see the directivity or we can see the gain. Okay, so we can, if you see the gain here, so the gain is coming around 1.5 dB. Okay, it is a linear scale. You can take here 10 dB, so the gain is coming 2 dB at max. So better to see in the linear, not to make it any complex. Let's see the linear value. Okay, and we can see the directivity also, in terms of directivity also. So you need to know what is directivity and what is your gain of the antenna. Okay, next is we can see here use power input. So power input is given 1 watt, so you can increase the power input also. If you increase the power input, then what will happen to the gain, what will happen to the directivity, that also can be seen here. Okay, we'll make it default, which is taken always as 1. Okay, so this is the thing, this is the radiation pattern. So what else we can do here? If we can go to here node, so we can see the electric current also, and we can animate that. So we can see that the current is changing, right? So maximum current is at center and minimum current is at the end. So that is where the antenna is actually radiating. And here you see something is changing, that is the frequency, starting from 2.5 to 3.2 250 megahertz to 320 megahertz. It is changing continuously. So you can pause it somewhere and you can click one by one, so it will give you the values. Okay, so if I click, then 2.5, what is the current, 2 point, then 2.9. so like this you can increase and you can see the current values at other frequencies also. So these are all the plots you need to plot: SWR, input impedance, your reflection coefficient, and then your current and your radiation pattern, and that is what you need to analyze. So you should see that as per theory you are getting those values or not. Okay, so that's it for your dipole antenna. Thank you.